Welcome back to Calculus Conundrums over limits, and feel free to subscribe to my channel if you find these helpful. One thing I want to warn you about in this particular section, let me give you a little bit of history. Generally, limits are covered at the beginning of a calculus course, and then you learn how to find derivatives. And this particular rule that I'm going to show you actually requires you to know how to find derivatives to find limits using this rule, this LHopitals rule. So this is usually taught toward the end of a Calculus 1 course, and it's probably not even mentioned in a business calculus course. So just be aware that in order to use this rule, you need to know how to find derivatives. So if you don't know how to find derivatives, then just bookmark this video and then come back to it after you learn how to find derivatives. Okay, so let's get started. So LHopitals rule for finding limits. Now, this is going to be two parts. The first part, we're going to deal with limits that give us this form here, the indeterminate form 0 over 0. Okay, now you can read this definition, but basically all you have to do is, if you want to find the limit of some quotient, say you want to find the limit of some quotient, f of x over g of x as x approaches a, and let's suppose that when you evaluate that directly, you get the indeterminate form 0 over 0. Well, LHopitals rule basically tells you that if you get that form, that you can actually try taking the derivative of the numerator and the derivative of the denominator, and then taking the limit, and it will give you the same value as the limit of the original expression. Okay, now make sure you understand what I'm saying here. I'm not saying take the derivative of this quotient. I'm saying take the derivative of the numerator and the derivative of the denominator, and write it as the derivative of the top over the derivative of the bottom, and then take the limit. Okay, so it's best if I just go ahead and show you a couple of examples here. So the first example I'm going to look at is the limit of sine x over x. Now this is actually an important limit. It's actually proved in calculus that the limit of sine x over x is actually 1 as x approaches 0. But in that proof, they go about a long-winded geometric proof. But if you have LHopitals rule, it's pretty simple to show what the limit of this is. First of all, before we can use LHopitals rule, we have to make sure the rule applies. So let's see if I try to evaluate this directly, let's see if it gives me 0 over 0. Okay, so if I plug 0 in for x, I get sine of 0, which is 0. And then if I plug 0 in for x down here, I get 0 in the denominator. So I definitely do get this form 0 over 0. So LHopitals rule does apply. So all I have to do is take the derivative of the numerator, which is going to give me cosine x, and then take the derivative of the denominator, which is going to give me 1, and then try to evaluate the same limit as x approaches 0 of this function. Well, you can see that if I take the limit of cosine x as x goes to 0, I'll just get cosine of 0, which is 1, and so the answer there is simply 1. And that's it. That's how simple it is to do it with LHopitals rule. Now again, you can't use LHopitals rule on just any limit. It has to be a limit that leads to one of the forms, and one of the forms is 0 over 0. So let's look at this one. We have natural log of x over x minus 1 as x approaches 1. So if we were just to plug 1 in here, we would get natural log of 1, which is 0. And then if we plug it in the denominator, we get 1 minus 1, which is 0. So again, I get the 0 over 0 form. So the rule does apply. So all I have to do now is take the derivative of natural log of x, in other words the derivative of the numerator, and I'll get 1 over x, and then take the derivative of the denominator, and the derivative of x minus 1 is 1. So basically I get 1 over x over 1, which is just 1 over x. And then if we take the limit of 1 over x as x approaches 1, we just get 1 over 1, which is 1. Okay? Alright, now sometimes it's not as easy as those first two. So I'm going to show you one here that actually is a little more complicated. But first of all, let's take a look at the function. The function is x sine x over 1 minus e to the negative x squared. Now, if I let x be 0, in the numerator I would get 0 times sine of 0, which would just be 0, so I get 0 in the numerator. And then if I let x be 0 in the denominator, I get 1 minus e to the 0, so that would just be 1 minus 1, which is 0 in the denominator. So I do get this form 0 over 0, so the rule does apply. Now, these functions, it's a little more complicated to take the derivatives. Now, I didn't show you the work on these, but I did show you that basically I'm going to do what I did before. I'm going to take the derivative of the numerator. So you would take the derivative of x sine x, and you would have to use the product rule. And again, if you don't know the product rule or don't know how to find derivatives, then you really shouldn't even be in this section. Alright, so the derivative of this, if I apply the product rule, turns out to be sine x plus x cosine x. And then I need to take the derivative of the bottom function. So the derivative of 1 minus e to the negative x squared is actually 2x times e to the negative x squared. Now let's apply the rule. Or let's try to evaluate this and see what we get. Sorry, I didn't mean to say apply the rule, but let's evaluate it. So we get sine of 0 plus 0 times cosine 0. Well, sine of 0 is 0, and 0 times cosine of 0 is 0. So the numerator is 0, and then if I multiply 2 times 0 times e to the 0, I'm going to get 0 in the denominator. So look, I actually got it again. So I got this form again. So that means I can still do LHopitals rule. So we're going to do LHopitals rule again. So this time I'm going to take the derivative of this numerator, sine x plus x cosine x, and then the derivative of this denominator, 2x times e to the minus x squared. So again, you can go off to scratch paper and find the derivative of sine x plus x cosine x, and you'll get 2 cosine x minus x sine x. And then if you find the derivative of 2x e to the negative x squared, that's going to give you 2e to the negative x squared minus 4x squared e to the negative x squared. Now, I never said all these were going to be easy. So on this one, you'd have to find the derivative of sine x, then you'd have to find the derivative of this product, and then combine the like terms. And then down here, you're going to have to use the product rule to find the derivative. So anyway, now let's try to take the limit of this function as x goes to 0. So if I take the derivative of this function, here I'm going to get 2 times the cosine of 0, which is cosine of 0 is 1. So I'm just going to get 2. So I'll get a 2 for this. And then when I plug 0 in here, I'll get 0 times sine of 0, so I'll get a 0 there. So I'll have 2 minus 0. And then on the bottom, I'm going to have 2 times e to the 0, so that's 2 times 1, so that's going to give me 2. And then here I'm going to get 4 times 0 squared times this, so that's just going to give me 0. And so I'm going to get 2 minus 0 on top, 2 minus 0 on bottom, so that's just going to be 2 over 2, which is 1. Some indeterminate forms can be rewritten so that you can get them in the appropriate indeterminate form of 0 over 0. Like for instance, this one, 1 over x squared as x approaches 0 from the right is actually infinity, and 1 over sine x as x approaches 0 from the right is also infinity. So if you tried to evaluate this limit, you would get infinity for this, so you would have infinity minus infinity, and infinity minus infinity is another indeterminate form. So what we could do here is we could actually combine these two fractions by getting a common denominator, and so the common denominator would be x squared times sine x, and then for this fraction the numerator would be sine x, and for this fraction the numerator would be x squared. So I would get sine x minus x squared over x squared sine x. Now let's let x approach 0 here and see what we get. Let's say we would get 0 minus 0, and then on the bottom we get 0 squared times 0, so we do get the form 0 over 0, so the rule applies. So now I'm going to apply LHopitals rule. The derivative of sine x is cosine x, the derivative of x squared is 2x, and then to find the derivative of x squared sine x I have to do the product rule. So I'm going to get x squared cosine x plus 2x sine x. Now, if I evaluate this one, it doesn't give me a number. Let me show you what it gives me. If I plug 0 in here, I get cosine of 0, which is 1. And then if I plug it in here, I get 2 times 0, which is 0. And then on the bottom, I'm going to get 0 for this term and 0 for this term. So I'm going to get 0 on the bottom. So I'm going to get 1 on top, 0 on the bottom. So I get 1 over 0. Well, if it's going to 1 over 0, then it's either going to infinity or negative infinity. But since we're approaching 0 from the right hand side, you can actually show that this is going to positive infinity. So I would say that, so I'm going to say that the limit is simply positive infinity for that. So the limit doesn't exist, but we can say it's positive infinity. Now for this one, I have x times arctan of 1 over x as x goes to infinity. Okay, well let's think about this. This is, as x goes to infinity, this is going to be just infinity. And then I have arctan of 1 over x, so that's going to be arctan of, as x goes to infinity, 1 over x goes to 0. So that's going to be arctan of 0, which is 0. So this turns out to be infinity minus 0. Well, that's also an indeterminate form, but we can get it in our form 0 over 0 by just doing a clever little trick here. If we move this x to the denominator and write it as 1 over x, then it's really the same thing. So I'm going to move the x to the denominator and write it as 1 over x. And now, if I let x go to infinity, this is going to be arctan of 0, which is 0, and then as x goes to infinity, 1 over x goes to 0, so I get 0 over 0, and so now I can use LHopitals rule. Now, you'll need to look up the formula for the derivative of arctan of u, but the derivative of arctan of 1 over x is going to be minus 1 over x squared over 1 plus 1 over x squared, and then the derivative of 1 over x just minus 1 over x squared. Now I'm just going to take the minus 1 over x squared and flip it over and multiply it and make it minus x squared. And then when I multiply the minus x squared times the minus 1 over x squared, that's going to give me positive 1, so that gives me positive 1 right there. And then on the denominator, I still have the 1 plus 1 over x squared. And so now, if I let x go to infinity, the 1 stays constant as 1, and then the 1 over x squared goes to 0, so the denominator becomes 1 plus 0, which is 1, and so I get 1 over 1, which is 1. And that completes the first part of LHopitals rule. In the next video, I'll show you a second set of problems involving LHopitals rule.